Welcome to the ARSET training, transforming Earth observation data into building infrastructure data sets for disaster risk modeling. My name is Brock Blevins, and I'm an ARSET trainer based at NASA's Goddard Space Flight Center in Greenbelt, Maryland. It's a pleasure to welcome you all to the first part of this three-part webinar series. Before we begin, I will briefly inform you about the ARSET program. For those unfamiliar to the Applied Remote Sensing Training Program, or ARSET, ARSET is part of NASA's Applied Sciences Capacity Building Program. ARSET provides accessible, relevant, and cost-free trainings on remote sensing satellites, sensors, methods, tools, and applications, all tailored to audiences with a variety of experience levels. Our trainings cover a range of data sets and analysis tools and their applications to agriculture, climate and resilience, disasters, ecological conservation, health and air quality, and water resources. Trainings are offered online or in person, freely available to anyone with an internet connection, and conducted either live or instructor-led or asynchronous and self-paced. ARSET trainings have both bilingual and multilingual options and use only open source software and data. Since 2009, the program has reached over 100,000 participants from over 180 countries. We encourage you to visit our website and learn more about the program. All ARSET materials are freely available to use and adapt to your curriculum. If you use the methods and data presented in these ARSET trainings, please acknowledge the NASA Applied Remote Sensing Training Program. The following slides will provide you with an overview of this three-part webinar series. So, why is climate risk assessment important? Even with the drastic reduction in carbon emissions, short and medium-term impacts are inevitable. Climate change impacts and risks are increasingly becoming complex and more difficult to manage. Climate change impacts on human infrastructure are not well understood and vary drastically by location. So understanding community-specific risks to climate change is critical to evaluating adaptation strategies. By following the approaches described in this three-part training, participants should be able to recognize what building vulnerability is and why it's important to risk modeling, identify the core elements of natural hazard risk modeling and asset loss estimation, identify fundamental approaches for developing building exposure models using Earth observation data and tools, apply a basic procedure to model built infrastructure exposure and vulnerability, characteristics from Earth observation data, evaluate building-specific exposure data to identify key components for fit, validity, consistency, and rectify bias, evaluate the appropriate use of modeled building exposure data to a given community, apply strategies to identify and address equity and bias considerations, apply approaches to validate the building data with imagery from regional data sets, and document your exposure development process through metadata so that others can understand the process used, the limitations, and how to update it if necessary. The prerequisites for this three-part training are fundamentals of remote sensing, which we have available on demand, and you can familiar through the ARSET program for those who are unfamiliar with some of the basics of remote sensing, or if you have equivalent experience, that's fine, but also a basic understanding of disaster risk management. So a quick review of prior knowledge. So just to know that climate change science tells us about the regional climate. Hazard specialists tell us about the hazards. GIS and Earth observations give us an idea of where that exposure is. And engineers tell us about the susceptibility to damage or vulnerability. And together, these can give us risk or likelihood of an impact. And for this, GIS is critical. GIS provides a digital glue between the disciplines by evaluating new sensors, technology, and data sets, understanding and communicating key GIS concepts and limitations, and then fusing, harmonizing, and assessing quality of multimodal-based data. Over the next week, there will be 3 2-hour parts that will include presentations and question and answer sessions. All materials and recordings from each session will be available on the training webpage, usually within 24 hours of the live session, so you can go back and review before the next one. Additionally, there will be 1 homework assignment that will be posted on October 10th, the last day of this training series, and that will have a due date of October 24th. This will be in the form of a Google form. A certificate of completion will be awarded to those who attend all live parts and complete the homework assignment before the given due date. Which brings us to part 1, where we will cover the development of regional exposure data with Earth observations. So the objectives for part 1 is that by the end, we hope that participants will be able to recognize what building vulnerability is and why it is important to risk modeling, be able to identify the core elements of natural hazard risk modeling and asset loss estimation, and also identify the fundamental approaches for developing building exposure models using EO data and tools. Please put your questions in the question box and we'll address those at the end of the webinar. Feel free to enter your questions as we go, and we'll try to address all questions during the Q&A session. Any remainder of questions will be answered in the Q&A document, which we will post to the training webpage about a week after that part. It is now my pleasure to introduce the guest trainers for today's webinar. Charles Huyck, Executive President of ImageCat. Gengiana Esquivias, Geospatial Analyst for ImageCat. And Mike Huyck, Project Engineer, also with ImageCat. We are delighted to have them joining us as guest trainers to discuss the development of regional exposure data with Earth observations. Charlie, over to you. Thank you.
All right, thanks for coming today. We're going to start with an explanation of what exposure data is and how it's used in the loss estimation process. So first of all, when people think about exposure data, they generally think about these type of architectural renderings or things that you see in movies, video games that imply quite a bit of detail about what might be going on the inside of a building, but are actually essentially just drawings, CAD drawings, and that type of thing. I've never seen these be able to be repurposed or used for the type of things that we're talking about. That's generally a whole different level of data. What we're talking about is the general building exposure data that's typically on an aggregated basis or a building specific basis that will give you things like a structural type, the vulnerability, the replacement cost, or the type of rough characteristics that you need for risk analysis. So it's something quite different. So what we're talking about is exposure data used for disaster risk reduction. We call it loss estimation, risk modeling. Sometimes you hear CAT modeling used. These are things that are used to essentially help nations try to reach their sustainable development goals. And there are kind of 4 main categories that you can think of that you might use these data. Before an event happens, for planning scenarios, what happens if a Category 5 hits Miami or New York? What happens if a magnitude 8 earthquake happens in Los Angeles, or there's a 500-year flood in the Midwest? These scenarios are used, they actually sort of play them out, bring together teams of folks from state, local, federal, tribal governments to pretend like they're responding to an event to figure out where there's gaps and what they might do better to respond in the future. During events, something is actually happening. What is it going on? What should we do about it? Should we evacuate an area? Should people be boarding up their windows? Is this hurricane going to hit Maine or Boston? This kind of thing. And if it does, if it goes this way or that, what are the possible ramifications after an event? So an earthquake has just happened, for example. Is international help required? Where there's the most damage? Where should we be deploying resources in search and rescue? And then on average, so you've run a single scenario. gives you kind of that single event view. But if you run suites of thousands of scenarios, you can kind of see what might happen at the annualized level, the 100-year level, the 500-year level, and you can use those to make decisions about things like retrofitting or insurance premiums. So what we're talking about is the field of disaster risk reduction, represented here on the left, which has been going on for at least 100 years. On the right, we've got a new field called climate change adaptation, and there's intersections between the two of them, and that's getting, they're more and more enmeshed as we begin to understand tactically on the ground what the probable effects of climate change can be and how we should go about responding to those climate changes. But unfortunately, we've got two different disciplines with two different lexicons, and we use words that are similar in very different ways. So in disaster risk reduction and disaster risk management, the concept is to reduce the impacts of disasters through preventative measures that people do. Climate change adaptation is, we talk about adaptation, which is making human-driven adjustments, the ecosystem, a policy, or processes to respond to changes in climate. So we've got different kind of stated goals there. In disasters, we talk about mitigation in terms of lessening the probable impact to a community, a society, a system, a building, by changing the attributes of that building, or it can be social policies or public awareness, but in general, changing something that has an impact on essentially the vulnerability. And mitigation in climate change policy, mitigation is defined quite differently. And is used for the reduction of greenhouse gas emissions that are the source of climate change. We don't use mitigation in that same context. So there's some confusion there sometimes. And likewise, vulnerability. Vulnerability refers to the physical conditions of a building or socially vulnerable class of people that essentially says, you've got an excitation, what will probably happen in terms of damage or impact. It's the inherent properties of those of that system, whether they're exposed to the hazard or not. Whereas the vulnerability in climate change adaptation really refers to things that are in a hazardous area. So whether or not you're which is sort of what we would call the risk, right? It's not the inherent properties of the system, but it's because you've got exposure in a hazardous area. So we're talking about a very specific ontology here, if you will, where we've got three kind of pillars: the hazard, the exposure, and the vulnerability. And I'm going to go through them one by one, but it's possible, for example, to have exposure and vulnerability, but no risk because there's no hazard there. For example, my house would fall down if it was hit by a 20-foot wave, but it's just not going to happen because there's not the hazard there. So there's not the risk. So hazard tells us things such as where things are likely to happen, how strong it is, the intensity of the wind speed, the depth of the flooding, the ground motion, how often, when with a forecast, what the duration is going to be, how long it will be exposed to a given wind speed or a given depth of flooding. And you're all familiar probably with these type of hurricane maps or 100-year flood maps. All of these impact just the effect of the nature on the ground, so to speak. And there's lots of different parameters ways that they can be expressed, but that's all kind of the hazard area, the natural phenomenon, if you will. Now, when we talk about vulnerability, particularly when we talk about building vulnerability, how likely is that building to fall down or be damaged given a level of hazard? So if the wind is so strong, how likely will it be that the envelope will be compromised and the wind will go into the house and lift the roof up and fall over? Or given the flood waters are 5 foot deep, what's the percent damage likely to be to your home? These are kind of expressions of vulnerability that are independent of the occurrence of the hazard. And then we put this all into a risk paradigm. So we've got the exposure, which we'll be talking about quite a bit. That's on top of this slide. That goes in with mapped to vulnerability. These vulnerabilities are things that they develop through testing or empirical classes. These very, very specific functions, damage functions or vulnerability functions. Cross-reference that with the hazard. You do your calculation, and that gives you some sort of loss or probability of loss that enables decision support. And there's two kind of main pillars of the risk analysis that we talk about. We talk about deterministic or scenarios, which is sort of a single event, one sort of time slice, or it could be multiple time slices for a hurricane if it's approaching, that kind of thing. But it's essentially running one framework. This is one loss scenario. But there's a probabilistic analysis that we refer to in this context. Typically, the probabilistic is referring to having a whole suite of events to figure out what the loss might be over time. So here we've got a curve, an EP curve, they call these. So given a return interval, that would be, you can see here, a 10-year event, a 50-year event, a 100-year event. So that's sort of a piece of the deterministic puzzle that slices into that probabilistic, how much loss you would expect to have experienced to a system or a building given the vulnerability. So this is what's used to make probabilistic decisions. So all of this kind of feeds into the disaster risk reduction framework that tries to help nations meet their sustainable development goals. There's a more kind of disaster specific framework, the Sendai framework, where they have specific metrics that come more directly out of the risk assessment, but you can map those to the sustainable development goals. And countries are trying to do that in order to reduce their losses, particularly in the face of climate change. So although the climate science is different than the disaster science, more and more we're understanding what those impacts are. And what we're doing is we call it climate conditioning the models so that we can understand how that's changing on the ground. So back to exposure development. What is building exposure in the context of disaster risk reduction? So here we've got 4 different pictures depicting 4 very different ways that people live. Very high-rise residential construction, informal, what we would call informal construction or unengineered construction, though very impressive hut here on the upper right. Very typical apartment building blocks, in this case, on a very high hazard area, and that it's set on a hillside, and then very typical single-family residential probably American construction, modern engineered structures. So a lot of what happens is what we're trying to do is characterize for a given area, a given census tract, a given cell, what the number of buildings are, where is it, that's depicted by the cell itself, by structure type, by costs, for the purpose of assessing that. In this context, what we find ourselves doing much of the time is saying, given a number of people, a population grid, for example, how many households are there? And given those households, what's the dwelling area? And how does that change through time and through space? So it's often more of an art than a science. A very large data fusion exercise where you take as much as possible the data that's in and make the best decision for distributing that out, minimizing bias in the process. So that's what we'll be talking about in detail over the next several days. So in that context, there's certain questions that we can answer, and then there's things that we really can't answer. We've gone through kind of generally what we want to do, but we can say yes, with this type of process, we can assess whether it's cost effective to retrofit certain building types regionally. Where should we focus our retrofitting efforts? Where should we get started? Where are the riskiest areas? Are building codes cost effective? And where are they cost effective? What might happen given a different specific event? What just happened for a specific event? But it does not tell us, is it cost effective to retrofit this specific building? Or which buildings fell down after an event? Which homes are flooded? exactly how many buildings fell down. And it's important to emphasize this because it's very easy for people to have false precision that comes out of these models, and it's important to keep reassessing what's a valid decision here and what's not an appropriate decision for this process. So here's some examples, some products that we've produced in the past, some projects that we've been involved with. One is the estimate of fatalities after the Nepal earthquake. Here our client was UNICEF, and they were looking to reach out to orphan children for the purposes of life safety and finding shelter for these folks. And we were able to produce a very wide area estimate of what the fatalities would be. With an idea that would correspond to where orphan children were. A high-profile example in the United States, a effort funded by Congress and managed by FEMA. We did the work with a National Institute of Building Sciences and a team of experts, which basically established how cost-effective it is to mitigate for given hazards, both to code and then above code. And this is a very high-profile project that's been, referenced by President Biden, used in hundreds of subsequent studies, media, and so forth. And it helps kind of promote awareness of the cost-effectiveness of mitigation. And all of that was done with a background of exposure data. Another example are cat bonds in developing countries. Mexico had a cat bond for earthquake, which they hit the jackpot twice with 8.0 magnitude earthquakes, triggering a release of hundreds of millions of dollars that allowed them to get back on their feet, distribute that to their people in their countries. And, the faster that money gets out there, the quicker that they're able to rectify the problems and get the economy going and avoid cascading effects. A very well-known phenomenon in disaster science. And if they, hadn't done that, then they would have to figure out where that money was going to come from. They would have to presumably argue about it from a policy standpoint, maybe take the money from somewhere else or ask the international community. So they didn't have to do any of that stuff. So all of that gets deployed right away, and that helps folks get back on their feet. And this is seen as a probable template for developing countries that don't have an insurance infrastructure to help, particularly where you've got the exacerbated effects of climate change, with drought and flooding. In Africa is an example of good candidates for cat bonds. So we'll just touch on the limitations here. We've got a whole presentation here, but it's what comes out of these exposure databases typically not accurate at the cell level, particularly if you've basically inferred this from population data. It cannot be more accurate than the original base data sets that go into it. If you've got problems in that base data with ethnic minorities, for example, that might not be considered or undercounted in the population data, that's going to be reflected in your exposure data. It can be a big problem. And it cannot expect that it'll always capture small unmapped rural areas. And this is a consistent problem in mountainous regions or in areas that remote sensing isn't good at capturing. For example, areas with low night lights sometimes are difficult to capture. There's a lot of cloud cover or tree canopies. All of these make it very difficult to find rural communities that might be impacted by large disasters. And lastly, these data sets, it's not good to repurpose them for civic purposes, such as a tax assessor database. These are built for purposes for loss estimation and do not provide the kind of building level accounting that you typically need for government purposes. A lot of challenges in putting these data sets together. One is data availability, trying to get access to data, permission to use the data once you've found that it's available. There's processing challenges, which we'll be going through, but having the skill set to do that at the city level, there's not a lot of cities that have that. Bias that are in the various parts of the data sets, which we'll be talking about in detail. Human error processing this data, it's very easy to make mistakes and difficult to catch them until you've got the risk estimate and people say, hey, what's this? Do you really think this? And that can be a big problem. Data gaps, you're not always going to have all of the data that you would like to be able to put these things together. You have to make assumptions and extrapolate through those data gaps. There's misperceptions about what the data sets are. There's misperceptions about the accuracy, and they're used at the building level, which is a false precision problem. Explaining the data with clarity is always a challenge to folks who might be high level and have short attention spans. Inappropriate legacies, you develop the data and you give it to folks and they use it for something 5 years later. They didn't hear the initial conversations perhaps because the original people that the data was developed for got new jobs, or the people that produced the data got new jobs, and then just the data getting old and dusty. All of these are very big problems, which we'll be touching on as we go through, but things that you have to be cognizant of. A lot of these aren't different from the regular project work that all of you have probably been involved in, but things that need to be tracked and recognized nonetheless. Lastly, a challenge is advanced technologies. You've got artificial intelligence, which is exciting on one level and scary on another. Being able to apply it towards building level decisions, for example, it's probably not appropriate. UAV data, additional sensors. There's sort of, I think, a thrust in the GIS community to get higher and higher resolution on data, but higher and higher resolution data does not mean more accuracy. And it might mean spending more money developing building exposure databases in GIS than is warranted for the risk assessment that's being developed, given the massive amount of uncertainty that's generally in the hazard data and the vulnerability anyway. So those are all kind of things that you have to think about for having a balance here, and things that we'll be talking about over the next 3 days.
Hello everyone, I'm Gengiana Esquivias, the Geospatial Analyst for ImageCat, and today I will be discussing the basic process for developing building exposure databases. I will go over these 3 basic concepts for developing a building exposure database. First, I will discuss what are the different types of building exposure levels. Then I will explain what data is required for developing the exposure database. And throughout the presentation, I will be giving examples of how Earth observation data or satellite data products are used. For the past decade, we have developed a taxonomy and classification system for 5 exposure level types. These levels are defined by the spatial scale of the input data and communicates the level of detail, content, and method required for producing each exposure level. Level 1 is a rapid, large-scale building exposure analysis, which primarily sources Earth observation data, trusted global resources, and aggregated demographic and housing data. Level 2 consists of national-level structural distribution information, economic parameters, general and essential facility building stock, demographic data from National Statistical Institutes or census. Level 3 requires a significant effort in order to refine national level data to reflect regional or subnational trends. An example would be incorporating climate or cultural regions to better represent the varying construction patterns in each. Or level 3 can be used to identify large urban areas where building footprint data is used to adjust building counts and built-up area estimates. Level 4 consists of a building-specific dataset aggregated either to a uniform grid, a fine-scale administrative unit, or another boundary smaller than the subnational level. Although the users compromise the spatial resolution of the available data by aggregating it, this method allows for a more accurate representation of the building exposure by reducing the noise in the data. And finally, level 5 is a building or site-specific exposure database. This exposure level requires an adequate amount of building-specific attribute data in order to characterize risk and vulnerability for each location. In this example of the County of Los Angeles, we can see how the building exposure levels differ based on the input data required per level. In this comparative analysis, we came across some unexpected results, such as those found in level 1 and level 5, where in spite of the vast difference in their spatial resolution, these two had the closest total exposure value to one another and the lowest of all the other levels. And when we detrend the results, we saw that the total exposure values for levels 2, 3, and 4 were very consistent to one another. This could be due to the fact that although there were regional adjustments made to level 3 and 4, the primary source for each was the HAZAS database and vulnerability curves. This is especially important for the modeling community to understand because it highlights the fact that an increase in data resolution does not necessarily mean that there will be an increase in precision or accuracy. This exercise allowed us to identify key parameters that significantly affected the output of the results. Those parameters being persons per household values, living area per household, replacement cost values, and exchange rates. Another important takeaway from these 5 exposure levels is that the degree of uncertainty within each level greatly depends on the quality of the input data. So the analyst must be meticulous in documenting their data sources, methods, and validation process in order to reduce the introduction of errors into the data, especially for exposure levels 3 and up. Therefore, it is important to understand the methods and data required for processing these 7 steps. For estimating building counts and number of people, having accurate and high-quality data is essential. For exposure level 1 and 2, typically the population, persons per household, or number of households are used to estimate the number of buildings given an average area per household value. While in level 4 and 5, the building count data is more typically used to estimate the number of people. And for level 3, land use data or development patterns are used to refine and reallocate national level population and housing data to the subnational scale. For estimating the number of buildings and built-up area, you can use census or microcensus housing data, open source building footprint and height profiles, and Earth observation-based data products. We have found that there is a positive correlation between the number of households and built-up area. So using a sample of building footprints, heights, and number of households, we can train a model to produce total building counts and area estimates that are supported by the census data. The level of detail of these estimates will vary depending on the exposure level of your study. For example, a level 1 may simply categorize the building counts and total area by an urban-rural designation for the entire country, while level 3 could report these values at a 500-meter grid cell by development pattern type. And a great place to find various EO-based built-up surfaces and population data is the NASA PopGrid viewer. If there isn't any documentation or existing building footprint data for your study region, building counts and built-up area can be extracted from high-resolution satellite imagery or aerial photography. This can be done through traditional remote sensing techniques such as a supervised or unsupervised image classification analysis, or with the newer machine learning neural network or automated image segmentation algorithms. The image to the right is an example of a supervised classification analysis where the orange pixels represent the building perimeters. These perimeters can be converted to polygon building footprints. And the image to the left shows how the panchromatic image can be used to determine built-up area density and later classify the image by density zones, which could represent single-family residential areas or high urban areas. And using the extracted building footprints as a sample set, we can extrapolate and estimate number of buildings and built-up area. As with the building footprint extraction, we were able to use Earth observation-based data products for determining building heights. This is an important attribute to obtain because the total living area value is one of the key parameters that directly influences the total building exposure value. What this means is that if we only use the building footprint data, then our building exposure values would be underestimated since the values are based solely on the area and not the built-up volume. Building heights can also help determine building distribution estimates. In these images here, you can see how we use Sentinel SAR data to estimate the building heights based on development pattern signatures found in the mountainous region of Nepal. Without this analysis, the pockets of mid-sized towns with 2 to 3 story buildings would have been assigned as a rural single-story construction. The method for estimating building distribution by development pattern types typically begins with an engineer identifying local construction types for the study region, either through virtual reconnaissance, through available street view imagery, or through an in-person survey. Once the construction types are determined, homogeneous construction type zones, which we call development patterns, are classified, and we begin to create delineated sample polygons for each type. The spatial scale of these delineated polygons will depend on the level of effort and exposure level required for your specific study. This can span from a simple small-scale delineation that only classifies the urban-rural zones, or it can range to a very detailed large-scale mapping unit as seen in the right-hand side image of San Jose, Costa Rica. Prior to the development pattern delineations, the building and population distribution for San Jose would have been evenly distributed throughout the administrative unit. But now the buildings are reallocated to the regions that are more consistent with the on-the-ground observations. Development pattern segmentation allows us to get a better understanding of where people actually live, and we can improve the structural distribution estimates and local mapping schemes, all of which is important for disaster risk modeling and mitigation planning because it identifies the vulnerable communities, vulnerable infrastructure, and potential risks to important supply chain facilities. Prior to the use of development pattern segmentation, our understanding of a region was limited to an urban-rural designation that can be seen in the bottom right-hand image, the red being the urban and green being rural. When analyzing risk, we would be limited to using the default vulnerability curves associated to that urban-rural designation. Additionally, you can see that the urban class was overestimated and industrial development pattern types are buried within the data. Now, in the upper right-hand corner, the image shows how the development pattern segmentation is able to classify the different degrees of urbanity, and it highlights locations of crucial manufacturing and industrial locations. Once the development patterns have been determined, a structural distribution can be estimated using a combination of virtual reconnaissance, building construction literature, and a well-defined stratified sampling strategy. For a level 1 exposure, you can use global datasets like the World Housing Encyclopedia, whereas for a level 3 or 4, you'll require an in-field survey to sample the structural types within each development pattern. So how do we conduct a sampling strategy? We start by generating a set of randomized points and randomly select an even amount of survey locations per development pattern. While in the field, the survey team takes samples of the buildings found in and around that location, recording important building attribute information like building height, age, occupancy, and structural type. Then those samples are extrapolated to the similar development pattern throughout this study region. This method improves the structural distribution and mapping scheme of the study. Applications like the inventory data capture tool can be used to collect the field data and take geotagged images. As part of the USAID Prepare program, I traveled to San Jose, Costa Rica to give a workshop on the IDCT tool. The purpose of the workshop was to teach the professors, engineers, firefighters, and local volunteers on how to use the data collection tool and how to conduct a building inventory study for a seismic risk analysis. The wonderful part about this program and project was that the local community was able to take command in creating their own building inventory instead of relying on international groups. This allows them to update their databases as needed and utilizes the depth of knowledge from their local experts. After all the building and population data has been collected and the development pattern and mapping schemes have been created, they are all brought together as input data for the Monte Carlo simulation, which models exposure. This takes several iterations and fine-tuning of the parameters. For example, we check against the national demographic and housing data in order to evaluate if the output results are reasonable and do not exceed the known building count or population values. The results are also reviewed to resolve any over or underestimating within an individual development pattern type. For example, in Tanzania, we had to create a new special case urban development pattern type for the western portion of the country, because after the first iterations, we noticed a significant overestimation of high-rise buildings due to the sampling done in the urban areas of the towns to the east. After the validation process is complete, replacement cost values can be calculated using the estimated total building area, either for occupancy or building type, using various construction cost handbooks or local expert opinion. You may have to experiment with the different replacement cost values and compare the results, or you may have to use a combination of sources which are more applicable to different building types. For example, construction cost manuals may be an excellent source for a dense urban area with high-rise construction, but may be less useful for a rural area. In its place, you may want to review cost estimates from resettlement action plan reports because they might be better suited for scaling replacement cost values of adobe or earthen homes based on the durability factor of the building material. Adding essential facilities is critical for identifying vulnerable communities, at-risk lifeline services, and estimating the availability of resources or shelters in the case of an emergency. Although many humanitarian aid organizations have put in a significant amount of effort in developing more detailed healthcare and education facility information, many countries continue to have very limited data sets, especially those that contain geocoded information. Therefore, sampling and data fusion would be required, which can be time-consuming, but would bear fruitful for a disaster risk management assessment. To summarize, Earth observation datasets play an integral role in developing building exposure databases. Urban intensity datasets, which are impervious surfaces or built-up area data, have a strong correlation with structural pattern types, which aid in the development of structural distribution and development pattern classification. Global population datasets are very valuable for developing a rapid level 1 or level 2 building exposure, but you will need to review the accuracy of the data at your location and make adjustments as needed. Development pattern segmentation wouldn't be possible without satellite image composites of various sources, either from nighttime light data, impervious surfaces, land use, and various population grids. Or the composite can source satellite imagery and data products that have gone through textural or spectral analysis. Each composite combination can highlight various attributes. For example, dense urban areas can be seen as the white pixels in the bottom image. The covariance image analysis in the upper image highlights another method for extracting building footprints, specifically extracting large industrial facilities or closely grouped informal housing. The use of Earth observation continues to evolve, and I look forward in seeing what the new technology has to offer. Thank you, and this concludes my presentation.
Hi, my name is Mike Equcni. I'm a project engineer here at ImageCat, and today I'll be talking about the structural mapping scheme development and building sampling. In this presentation, we'll go over two of the main things required for exposure development. First are the development patterns. These are country specific. We'll go over what they are and why they're important. And then the second part would be the mapping schemes. These are basically the building taxonomies. We'll go through how they're defined and how they're developed. So what are development patterns? Basically, they're country-specific homogeneous regions of building types and densities that are created using remote sensing data. So essentially, each development pattern gets a unique distribution of the built-up environment. And the built-up environment can include properties such as the structural characteristics, what type of lateral force resisting system is it? What are the building materials? What are the different height profiles? So it can be related to number of stories. What's the distribution of occupancies? And these development patterns are, essentially created throughout the entire region. So they don't necessarily need to be contiguous. You can have rural in one part, separated by residentials, and then rural. And it's important to note that development patterns will differ by region. Just because you have, some type of development pattern in the US doesn't necessarily mean that you're going to have it in a different part of the globe. So why is there a need for these development patterns? If you look on the left, it's a satellite photo of LA County in Southern California. If you look on the top right, it's the land use occupancy, which is basically all residential. So if you were just to look at these and you ask me what's the built-up environment, I'd assume most of it's 1 or 2-story wood frame residential construction. What that neglects to tell you is that there are other parts, maybe it'll be downtown areas, the industrial areas, where that's just not the case. So the purpose of the development pattern is to capture that unique built-up environment building distribution. So since we know that LA County isn't all single-story, 2-story wood frame construction, we want to be able to identify those regions that are much different in regards to the built-up environment. So here we have a zoomed-in photo of some of these areas that we found in LA County. Bottom left is downtown LA. This is where the mid and high-rise reinforced concrete or steel frame structures are. To the top left, just to the west of downtown LA, are the 2, 3, 4 wood frame apartment structures. On the top is the industrial regions. These are large warehouses, single-story tilt-ups typically. Bottom right is a pretty unique situation with the LA port, or Long Beach and LA ports. And on the top right is typical single-story 1-2 wood-framed construction that you'll see in most of the suburbs of Southern California. So why do we want to, identify these unique areas? It's because each building distribution for each of these is quite different. And if we're looking at any type of hazard modeling or anything like that, we want to know these characteristics. We want to know the structure type. We want to know the height. Possibly we want to know the TIV. So the building development patterns will capture all of this information, and you'll be able to identify why it's unique, what's your vulnerability in a given location. So now that we know what development patterns are, I'll go through some of the ones that we typically see throughout the world. It's important to note that not every country is going to have all these development patterns. Some might not have those central business districts or high urban areas, which we'll go through later. But here are some examples that we typically see. So the first one is rural. Most countries are going to have this. These are found outside of the city boundaries. We usually associate them with agricultural regions. In developing countries, these are usually small remote villages, one way in, one way out, and they're usually 1-2 story, non-engineered, using local materials and construction techniques. So next up, we have the residential development patterns. These are pretty obvious. They're mainly 1 and 2 story, single family, detached homes, probably local materials, construction methodologies. One thing you'll notice here is that, one of these cells is blank. That doesn't necessarily mean there's no residential regions in the house, in the area. It's just that there is no construction pattern that met all our requirements for the residential development pattern. Residential occupancies probably are going to fit into another development pattern. Next is what we're calling high-density residential development patterns. And these are typically found in and around the urban centers. You'll notice things start getting a little more dense, maybe a little taller with each development pattern. But a majority of the population here, lives in multifamily residential housing, apartment structures. Still, we're looking at low rise with some occasional mid-rise rhythms. Next up, we have the urban development patterns. These are exactly how they sound. They're found in and around the major city centers. Space is limited, so buildings are pretty tight, and they're fairly regular in shape, just to fit within the block. You'll typically see these as low to mid-rise residential. This is where you start seeing a lot of the commercial come in, with the occasional high-rise, office building or apartment structure. So here we have one step above the urban development pattern. It's what we're calling the high urban. These are found only in the major cities and they're typically the central business district of the region. They're occupied by mid to high-rise buildings. You can see from this satellite image, how densely spaced it is. You can see how tall they are from the shadows, and just the angle of this image. There's 3 lengths here. Again, not every country's going to have it. So this is why we're going to start seeing phasing out of this development pattern in a lot of the more underdeveloped areas. The last of the typical development patterns are industrial areas. These are pretty obvious from satellite imagery, and they're usually, ports, mining area, other industrial activities. They're large warehouses, regular in shape. You can see large rectangular buildings basically in these development patterns. You'll also see some, low-rise office and commercial supporting areas, but for the most part, it's going to be warehouse structures. So here are some other special types that we've observed around the world. They're not going to be everywhere, but they will be there in some cases. The first one are informal housing. These are pretty dense informal settlements. And you'll usually find them around the edges of any major city. They're standalone structures, basically no space in between any of them. They're almost always unplanned, non-engineered, and what they'll do is pretty much use any local materials to create these areas. On the other extreme are these what we're calling very high urban areas. These are global central business districts, and those always high-rise buildings. Bottom right is Hong Kong. You just see the high profiles are much different. Sizes are much different than any other development pattern that we've gone through so far. So now that we know the unique development patterns, we need to be able to associate a mapping scheme to each of them. So mapping schemes basically give you a breakdown percentage-wise of the built-up environment. Mapping schemes can include, story height profiles, structural type profiles, occupancy, TIV later on. But basically, each development pattern gets this unique distribution for future analysis. For the mapping scheme basics, we'll go through 3 things. First, we'll show how to identify which structural types are in your region. And then we'll go over how to gather and organize any type of census data that's available. And lastly, how to construct these mapping schemes, building distributions, essentially. So the first thing you want to do in your country of interest, region of interest, is know what built-up environment can consist of. What materials are used, what's typical structural system. Things in the US are going to be much different than areas such as Nepal. So the first thing that we'll do is look at any scholarly or online journals, the World Housing Encyclopedia, any PDNA reports. And the good thing about these is they go pretty in depth of what unique buildings are, structural materials, a lot of force-resistant systems, the methodologies of construction, they're region specific, and they'll give you any known structural details, deficiencies, and details for future vulnerability modeling. So next we look at any type of country-specific assessments. This is usually in the form of census data. The census data is good because it gives a general overview of the country, and usually they provide, breakouts, percentages of materials, home materials, wall materials, roofing, flooring, etc. One of the cons is that, sometimes it's limited, this information, if you can get it, and that there's no distribution of the lateral force resistant system. They'll give you the main materials for things such as the walls, but you're going to have to use the information you gathered from your initial research to essentially assign these main materials to a structural system. When we look a little bit broader, we can use the global building exposure databases, such as this one from Pager. essentially they give a pretty detailed description of the structural type distribution for all countries in the world. There's a downside too that, it's limited to essentially rural, urban, and not all countries are country specific, meaning that if they don't have enough data for one country, they'll use a proxy from a neighboring country. So we have to be aware of using this type of data. In regards to documentation, what we'll lastly look at is building codes. These are good because they're country specific. And so they'll tell you any applicable materials and construction practices that they do use. The cons are, enforcement can and often may be limited. So what you see in the code might not be what you see out in the field. So you have to be careful with your vulnerability modeling if this is the case. So one of the things we heavily rely on for identifying the construction types or any type of ground imagery or videos, mainly Google Street View and Mapillary. The pros of this is that, they're widely available and often pretty good quality. Some cases in post-event, there'll be some damaged buildings, so you can get images of the building materials, maybe some structural types. Another advantage is if you use this in combination with satellite images, you can start making some correlations between, I know it has this type of roof, this type of slope material from satellite image. I know it's the structural type from the ground view. So now you can start making some assumptions based purely on satellite images at that point. The cons that they're often pretty limited in rural and maybe more developing countries. This is when you're going to have to start looking at, online photo sites or videos to get any good idea of what the built environment is. So the point of this slide is to show you how to get from, a satellite photo down to a identified structural type. The top row, we have all our development patterns. On the middle row, we have typical buildings that we're seeing in the street view. And then this bottom row is where it's pretty advantageous for the street view, is we'll often see buildings under construction, which reveal the building materials and the structural system within the region, within the development pattern. So if you're not able to find some buildings under construction with the ground imagery, there's some other tips and tricks that we can do to figure out the structural type or building materials. This first one, I'll look at all sides. The back side doesn't have the curb appeal that they need, so it's often unfinished. So if we go to the back, you can see that, it's reinforced masonry building, which you can't really see from the front with the facade. Again, Google Earth has historic satellite imagery. You can toggle through that and see if you can capture when it was under construction. Here you can see it's tilt up. Google Maps also has a historic ground imagery. It's pretty recent though, so you're not going to go pretty far back. But here we're able to capture this apartment structure in Florida under construction. We can see it's a reinforced masonry block wall building because we're able to capture it under construction. So once we have a good handle on the construction types within a given region, we need to start creating these building distribution breakouts for each development pattern. And by breakouts, we mean what's the percent distribution of each structural type, what's the percent distribution of every building height, occupancy, et cetera, et cetera. For rural residential, we typically or heavily rely on any type of census or global data, depending on the resolution. So these are good because, Street View often is pretty limited out there, and they will provide percent breakouts by the wall material. We can't use that wall material for any vulnerability modeling. So what we have to do here, as in that bottom table there, is essentially map it to something that we can use, in this case, a pager. So using the knowledge you have of building materials, structural types, etc., that you learned from the previous slides, we are able to map directly the wall type to agent type for future analysis. For non-rural regions, we look for any country-specific exposure studies for mapping scheme development. These are usually done in high-hazard regions. For example, the one on the left is just in Tunisia. What it essentially was a field survey where they recorded the number of stories, structural type, age, occupancy. And so if we have that data and we have our development patterns, we can essentially overlay the two and pull mapping schemes directly that way. We, of course, do some sanity checking, again, with the street view, make sure that some of the assumptions are correct, and we'll redistribute the structural types or building heights based on our judgment of what we see on our review. If the relevant census data or the previously done field surveys are not available, we do a stratified sampling ourselves. This is both for the development of the mapping schemes and validation of any seamless mapping scheme that we already have. This can be desktop, which is both probably most of the time, or a ground survey, field survey team. So for example, on the left, we have our development pattern and we want to sample. We go through, identify each unique building, structural type, their height, etc. We do this a few times throughout the region to make sure we cover variations in the development pattern. From there, we essentially create these distributions that you'll see on the right side from our sample. So on the right, we have each unique structural type. We have each development pattern. And on the cells are our observations and our distributions of those based on our desktop study. So that was a summary on how we come up with the development patterns and how we create the mapping schemes unique to that development pattern. Just a few things in summary. First, do an online search, identify all the materials, all the structural types that are typical in that region. Once you have those, go through, Google satellite view, ground imagery, make sure you can find those and validate that those assumptions are correct. You definitely want to make use of any type of census data or region-specific or field surveys. It takes a lot of the legwork out, and they can help you with some preliminary mapping schemes. Once you have those mapping schemes, though, you need to be able to validate these, maybe through a stratified sampling. Again, the stratified sampling can be used to create the mapping schemes for those development patterns if we don't have any. At the end of it, I like to do a quick sanity check. Essentially, do these results make any sense? On the table on the left is development pattern 1, development pattern 2, 4, 5, 6. 7 is industrial, but 1 is rural, 2 is residential, 4 is high density residential, 5 is urban, 6 is high urban. So you want to look at it and make sure, do these height profiles make sense? Are there taller buildings where I expect them to be taller buildings, which is in the urban regions? Are the local materials, the wattle and daubs, the adobes, are they mainly in the rural residential regions? And again, on the opposite end, for the engineering construction, these reinforced concrete frame or steel brace frame buildings, are they in a region where I'd expect them to be, which is typically going to be in your high urban developed central business districts. And so with that, I'll leave it, and I hope you enjoyed the presentation and learned something from it. Thank you. I'll be presenting with my colleague Z, and we'll be going through this case study, which is a walkthrough of building exposure data from Tunisia. This was a project tasked to us by the World Bank, and essentially they wanted us to perform a multi-hazard study for the Republic of Tunisia, looking at both flood and earthquake risks. Our tasks included exposure development and a review of incorporation of a format suitable for loss estimation and also data collection. Guidance on vulnerability assessment assignments for both seismic and flood, assessment of the risk of the built-up environment, and a visualization within a BI tool. So the first thing that we did was identify all the homogeneous zones or the development patterns, which we talked about previously. This was pretty important for this country since it's kind of a mix between, older, vulnerable buildings and some of the newer developments that you'll see in residential or maybe some urban areas. So we identified 5 regions, 4 shown here. Rural is not shown, but what we have here is the essentially detached residential development patterns, industrial development patterns occupied by those large warehouses again. The urban regions, these are typically mid-rise buildings found in the city center. And then on the outskirts, you have these really dense, high-density residential development patterns, which are occupied by some of these more older, vulnerable structures, which we'll go into later. Once we knew what the development patterns were going to be, we needed to assess the built-up environment, essentially asking the question, what type of permitted and also non-permitted construction and building materials are prevalent throughout the country. We relied heavily mainly on 3 things. First was ground imagery. This was pretty limited through Google Earth, but there definitely was some ground imagery we used for validation and assessment. The census and housing data, that we had the Tunisia housing profile from UN Habitat. We also looked at Pager for some general building distributions. And finally, we had these country profile studies, which go into pretty good detail regarding the structural types, structural distributions for different parts of the region. So we were able to get this national catastrophe risk profile from the World Bank. This was pretty advantageous in 3 ways, essentially. First of all, it gave us the structural types that are prevalent within the country. It was in French, which we translated. It gave us distributions for the rural and urban areas for residential and non-residential construction. And it also gave us these vulnerability curves seen in the bottom right for each of the structural systems that they identified. So given those different lateral force resisting systems from the national risk profile, we needed to be able to identify them visually for both sanity check and for validation. So what we did was we used the limited street view imagery and any online photos to essentially identify and label each of those types that you see here. Next, we looked at census data from the World Bank and Ernst & Young. This detailed census data provided the foundation for the mapping schemes of the predominantly residential development patterns, as the data provided a breakout of the different types of housing. From the top left, you can see it's traditional, rudimentary, semi-detached villas or apartments. Structural types for these housing were not provided. Therefore, we had to rely on descriptions laid out in the Tunisia housing profile, which we'll go through after this. But this was beneficial because it gave us breakouts of these housing types for every governorate. And so we started looking through all these governorates, and some of them were solely residential or solely HT residential. So we could start using those as the preliminary mapping schemes for some of these basic development patterns. So the World Bank and Ernst & Young census data gave us 5 different housing types that are found within each governorate. The problem is we didn't know where they were, what they looked like, what kind of structure type it was. Thankfully, we found this Tunisia housing profile from the UN Habitat. And in it, they go through each of the 5 different types, and they even have a satellite photo of what these typical types look like. So what we're able to do is find these types in satellite imagery, Google Earth, use street view imagery to assign a structural type to it. And given those structural types, we assign them back to the World Bank distributions. And so from there, we can create these residential development pattern mapping schemes. So this was predominantly used just for those residential development patterns. Another source relied on was a study from the University of Tunis. And essentially what they did was they inventoried certain blocks within the city of Tunis and had an assessment of their vulnerability. You can see on the top which buildings were surveyed, and this ground survey it recorded quite a few things, which was the structural type, the occupancy, when it was built, the number of stories. And we use this for the non-residential statistics, since we already had a lot of residential stats from census data. This was great. It was direct observation and a breakdown of structural types for this downtown urban region. And this was suitable for our urban development patterns. So where we didn't have any census data or field survey data from previous studies, we needed to do essentially a stratified sampling strategy to come up with these mapping schemes. This was mainly what this is only done for the industrial development patterns. Although, it's the Ernst & Young and World Bank data provide a number of lots and lot sizes, there's no information regarding the structural type. So what we had to do was survey these regions throughout the country, and we recorded both the number of stories and the associated structural type using the information that we already had from the previous studies. So we ended up coming up with this distribution for industrial development patterns seen on the top right. So we used all the census data, field survey data, ground imagery to essentially come up with this nationwide mapping scheme for Tunisia for each of these 5 development patterns: rural, residential, HT residential, urban, and industrial. To recap, for the rural residential and HT residential, we relied heavily on the World Bank and Ernst & Young census data. These gave us the distributions by government. The Tunisia housing data allowed us to relate those housing types to the Ernst & Young building types. For the urban, we relied on the field survey from the University of Tunis. We did validation, inspection on our own to essentially sanity check any of those results. And for the industrial, again, it was a sampling strategy. There's no information regarding structural types for this from anything that we could find. We needed to make sure these are all consistent. So we used the structural types seen below in French, apologies. But anything that we got from the Ernst & Young or the University of Tunis or from our sampling, we had to essentially map to one of these structural types. So that it's all consistent across the board. So we ended up with this mapping scheme seen below. And my colleague Z will go ahead and essentially tell us how we used all this information.
So once the development patterns were ready, so we used a machine learning model to classify development patterns across the entire country. So we took those digitized regions and we used that for training to create that model. And we did that in Google's engine platform. We chose that because first it had a lot of different data sets. We were using Landsat, we used spheres. We also used classified layers. One layer we used was global human settlement layer. So all those data were easily available within the platform. And also, second, it's very easy to pre-process that data. So we're stacking all that data. We had to resample some of the data because of different resolutions. We're stacking that. We did some normalization. So all of that was very easily done. Then they have built-in learning models. They have some different type of algorithm that we could test out to generate the final model. We could do the testing of the performance of the model within that platform. And once we did that, the final classified grids were exported into a TIFF that we use for the next step of processing. And the TIFF that we created was at 15 arc seconds, which is close to 0.5 kilometer resolution. So here we see the classifier layer overlay on the city of Tunis. And here we see the different colors represented the different development patterns. The yellow color represents the urban development pattern. We can see that in the city center. Then across that, we see a lot of these more cyan, bluish color dots, the residential. Then we have this little purple. Those are the dense residential. So we see these zones to be classified. And out of the city, we see the rural pattern, which more the brownish color. Here we see an example for another city where we have a lot less of the urban development pattern, but a lot more of the residential and dense residential. So with the grids classified, we did the exposure disaggregation. Here by disaggregation, we mean to geographically distribute the exposure onto these grids. Okay? And the data that we got from Ernst Young, the original exposure data, those were aggregated at the admin level. So here we used the remote sensing signal for each of these classified grids, and we distributed that geographically proportionally. And then we also vary the proportion depending on the different development patterns. Because at different development pattern, the total amount is quite different. In the replacement value for those amounts were also different. And then we apply these mapping schemes to represent the vulnerability. So at the end of that, we have the different grids. For each grid, we have the total amount of exposure represented, like number of buildings, we have the total replacement cost, and a series of vulnerability and the proportion of vulnerability that characterizes that exposure for every grid. So we did that analysis for the general, residential, commercial, industrial. We also did that for some quite specific one for education, financial, health, tourism. And for some exposure types, this method we did not apply. For the point-specific ones, like poor, dams, these are the disaggregation method does not apply. And also for some other one, we did not have damage functions. We also did the exposure refinement for some areas. And so this is to better characterize the flooding. So the original grid, remember, it was close to a half kilometer, which is adequate for earthquake analysis, but this is too coarse for flood modeling, especially because we had flood data at much higher resolution. So you can see from this picture, if the red color represents the area of a grid, the flood region is actually smaller than that. But if we're using this entire grid as the representative exposure, all we can do is just say the entire region is being flooded, which is not correct. Then also it's not really correct to assume that exposure is evenly distributed within that grid. So we use higher resolution remote sensing, and we did a higher level of disaggregation that gave us better grid resolution around the rivers, near river area or area that represented in those flooded areas. So we have better representation of the exposure at 90 meters. So we can have a better understanding of the flood risk. Now let's talk about the hazard data used. For flood, we use fluvial defended, fluvial undefended. Both of these are from inundation caused by rivers. And defended, undefended, the difference is the presence of defenses along the river, like flood walls or barriers. Fluvial data, those are inundation zones caused by excessive rain. So we had data at 90 meters. That's where we did the disaggregation refinement. We had the refinement for 90 meters, and we had flood depth for 10 different return periods. And so each of these return periods could be converted into a probability that helped us in the end to calculate the annualized average loss. So for earthquake, we had a data which a lot more coarse, as you can see from that, but we had it for the entire country. And the metric that we used was peak ground acceleration. And we had that for 7 different return periods. The next step is to calculate the loss using the return period, hazard values at every grid, and the exposure with the vulnerabilities. We're able to calculate the losses. So in the end, we kind of have a return period loss curve for every grid, for every occupancy. So we collapsed that return period curve into an annualized average loss. Remember, the return periods correspond to different probabilities. So that can be aggregated into an AAL for every grid. The AAL was also aggregated for each admin 1 unit. So the final step was loading all that loss information, the exposure information into a BI tool. And that was the final presentation of the result. And the BI tool was very useful because it was presenting a map. It had different charts and different ways of representing the data. And the best part is these are interactive. So people click on area that admin, the graphs gets updated with the value from that admin. Or if they want to see a particular occupancy, they can just click on the occupancy and see all the results being updated. So this concludes our use case for what we did for Tunisia.
Charlie, Georgiana, Mike, thank you all for your terrific presentations. So let's review what we covered here today. We discussed exposure data and how it's used in the loss estimation process, as well as a basic process of developing those data. Additionally, we covered structural mapping scheme development and building sampling, and ended with a case study involving building exposure data in Tunisia. On October 5th, in part 2, 2 days from now, we will continue with the discussion with the development of site-specific exposure data with Earth observations. We'll also be looking at developing building structure data sets and a case study used to characterize vulnerabilities. So we hope that you can all join us for part 2. Below is the contact information for Charlie, Georgiana, and Mike, along with links to the training webpage, social media. And if you enjoyed today's webinar, we hope you'll sign up for ARSET's listserv to receive notifications of future trainings, and follow us on various social media platforms for other relevant announcements pertaining to NASA's Earth Sciences. We'll now transition to the Q&A portion of today's webinar. Thank you. All right, welcome to the question and answer session. Thank you everybody for submitting your questions throughout the presentation. And we've been working as a team to address those. And what I'll do is I'll just dive right in. And for any of the trainers that provided the answers, please feel free at any time to unmute and go through the document with me. So I'll start with question 1. How is it cost effective to actually retrofit when you have to spend the extra time and money on customizing specific requirements?
I'm sorry, Brock, am I supposed to jump in here and answer the question? I thought you were going to read there for a second.
Well, I thought it might be best who actually provided the text here to kind of walk through it, and I'll capture anything else that you might add to the answer.
Okay, Mike, why don't you go ahead and start, and then I'll follow up the back.
Thank you, Mike.
Sure. Yeah, so how do we know if it's cost effective? Basically, you'll do a benefit cost analysis just to see if this retrofit is cost effective. So what we do is, we run through the analysis, we calculate the expected losses for the as-is building, meaning the non-retrofitted building. We'll go ahead, this is expected losses in regards to loss of life, injury, things like that. And then we'll do the same analysis for the building that is retrofitted. And when it is cost effective, your BCR, your benefit cost ratio, will be essentially above 1. So I put an example, if your seismic retrofit costs 10K, and through our analysis, we expect 20K in savings. That's a BCR of 2. We expect that to be a cost beneficial at that point.
Yeah, and I think that kind of embedded in the question is, how can it really be cost effective if you have to do a lot of custom work? It's kind of we don't just look at retrofits and that analysis. We look at the cost effectiveness of new building codes, the cost effectiveness of buyouts, actually removing homes from areas of high risk. But we also do sometimes look at specific types of retrofit, many of which, will require adaptation for specific buildings like trailer tie downs or retrofitting for earthquakes, but are fairly standard. So that the customization does not add a lot of cost to the project. And then in some projects, they'll be highly customized. And in those cases, those are usually cost effective in areas of high risk where you have life safety concerns or a lot of benefit costs. Business interruption concerns. So those are also included in the benefits of the BCA analysis Mike was talking about.
Thank you very much, Mike and Charlie. And for all the participants, please feel free to continue adding questions to the question and answer box, and we'll add them to this document, and we'll try to address as many as we can during our Q&A session. So please keep them coming. Question 2, what would be the possibility of exposure mapping in terms of accuracy of renewable energy to asset extreme events using EO data?
Yeah, so this it's difficult to answer that question without knowing sort of the specifics of the application. But this is definitely, exposure data is definitely being used to, assess transition risk. One thing that we've been involved with is looking at the vulnerability of new sites, placement of new sites, or the risk associated with solar panels. Accuracy is really going to depend on the specific application.
Great, thank you. Question 3, can you provide some articles related to how to measure building height and shade patterns in urban areas?
Yeah, it looks like the questioner is looking at trying to characterize heat islands. I've not done any work in the shade patterns myself. And in terms of measuring building height, it really depends on your base data and your application. I just would recommend going to Google Scholar. That's often what we do to start.
Thank you. Question 4, on slide 9, SAR was mentioned, synthetic aperture radar, when talking about building height. Sentinel-1 data has a ground resolution of 10 meters. What would be the vertical accuracy when using this data set for estimating the building height? Presuming picked up correctly that Sentinel-1 SAR was used to find that building height.
So this is a highly technical question that I don't know the answer to. Sentinel-1 was not used on that slide. That slide was actually just an illustration of the types of things that you can use EO for. That specific study was from quite a while ago and actually used airborne SAR data. I think that the resolution was about 3 meters. I looked into the accuracy of that data set for quite a while, actually, as a study, and we discovered that specific buildings might actually disappear in the SAR data, depending on the orientation of the building, what was on the roof, and so on and so forth. So we got unprocessed SAR data and looked into the accuracy ourselves. So there's definitely issues with trying to get heights from specific buildings from SAR data. That's not the way that we actually use the data typically. We will use it to come up with almost like a height profile for a region, which would be used basically to extrapolate structural characteristics in the methods that using the methods of developing development patterns that some of the other speakers addressed. So yes, SAR data for heights can be highly problematic.
Great, thank you very much for that clarification. Question 5, in the step of estimating the distribution of building by development patterns, identifying, delineating development patterns, how much effort goes into this process and can it be automated? Second question to that is there a global data set that has this information, or does it need to be calculated for each study area?
So, it's A lot of these, the answers to these questions will depend on the scale of the work that's being done. We almost never use automated detection algorithms. We almost always do semi-automated detection algorithms that will start with a long conversation with Mike and Z and Gengiana and myself, looking at the specific structural characteristics of the country and the risks of the country and what we think that can be extracted. So you almost want to start with some base knowledge to make sure that you don't miss anything in an automated process. Is there global data sets that you can use? Yeah, I mean, there's a lot of, there's the World Housing Encyclopedia from ERI. That's a great source for structural information. I believe Mike mentioned that. GEM has a global data set where they've got structural types. I don't think they have development patterns, but they have structural types. Pager has embedded structural types by urban and non-urban areas that can be used in conjunction with development patterns. And then the Meteor project by BGS that's mentioned here has 46 countries, developing countries, where we've provided that information.
Great, thank you. Question 6. I live in Qatar, which is on the coast of the Arabian Gulf. Our region is generally extremely low risk in terms of natural disasters, and thus we have tons of energy producing plants near the sea. Even though it's considered safe, we still need to take measures in the case of that 1%. What approach would be appropriate to address the what ifs?
Sorry, I can take this one again. Yeah, so if you're looking specifically at the risk to the power plants and energy generation facilities, the first thing to do is to start with the locations of those plants and then overlay your risk data. If you've got flood data, you mentioned 1%, getting a 1% flood hazard data set. There's international data sets that you can start with that are commercial. Fathom, for example, is a good source, JBA. And then overlay with the facility location and then use that to prioritize the acquisition of more high resolution data. If you're looking at very high value facilities such as this, though, you might not want to rely on 1%. You might look at the 500-year, the 2,500-year flood maps because, for one thing, climate is changing and it pays to be conservative. And on the other hand, it might be very cost effective to mitigate those high value properties that's, can have massive cascading, particularly if you're talking about, an energy generation and an energy generating economy there, that can be very disruptive to hopefully the economy of Qatar. So you might want to look beyond the 1%.
Great, thank you. Question 7. It's nice to learn about ongoing projects in Nepal for identifying building heights. The country has scattered buildings in hills and mountains. How can I estimate the number of buildings in such terrains with scattered built-up patterns? Further, for the use of local resources like slates, rock, or wooden or bushy rooftops make it even more challenging to detect buildings. Have you seen any similar work in this area?
Yeah, I mean, we've done a lot of work in Nepal. It's hard. And specifically, we use the mountainous areas in Nepal as an illustrative example of how hard it can be. That being said, we've done the best we can. We've developed both the level 1 and a level 3 data set for Nepal in order to kind of compare the two. Also on a project with GS for the Ukraine Space Agency, and OSM was on that project. If you're trying to get specific buildings, you can't beat the human eye and high resolution data. And that's actually what was done by OSM, given the magnitude of the risk in Nepal. I think they've had their kind of crowdsourcing engine digitize every building footprint, and that's a very good guess. And you can cross-reference that with population data sets and scale up if you need to, but I don't think you need to scale too much, maybe in some of those mountainous areas. So anyway, there are sources. The Meteor project, maybe one of my cohorts here can get the link and put it in there that you can take a look at.
Great, thank you. And it's nice to have a clarification that no, it can be a little bit difficult, and but there are some ways being developed to work around those. Question 8. When estimating raster cell population counts using building and other spatial data sets, have you come across known under forest canopy populations that are undetectable by remote sensing? If so, how did you account for those counts?
Yeah, so I mean, this is another limitation that we really want to be upfront with, and everybody on the call needs to be upfront with if you go down the road of developing these exposure data sets, and that is, you can't characterize what you can't see there. If you do characterize it, you have to be very transparent in how you go about that process, and that needs to be a limitation. If you, for example, have an area where you've got severe flood risk under a tree canopy, you're not going to be able to make very definitive statements about that risk. And that's something that you need to understand. I think we've got a whole session on that, actually, some of the limitations that you need to look at. And a good example is the PopGrid data, right? PopGrid is an effort led by CSIN, where they've actually mapped different global population data sets in the same screen so that users can see how different isometrically mapped assumptions about distribution of population can result in very different estimates on a per grid basis. So anyway, I mean, the question is sort of what have we done in those situations? I think, Papua New Guinea was a good example for us, where we had to kind of throw up our hands and rely on some more statistical methods. And in those cases, we acquired language spoken maps of tribes that could be very small, and used that to distribute the population. We were able to find clearings on coastal areas associated with farming and development. We placed a lot of population in those areas. And then I think that there was, in some areas that were internal to the country, we just made some assumptions about distance from roads. But it can be very difficult, and that's one of the areas that you need to be very transparent about.
Great, that's good to know. And we're trying to create a nice community based around these trainings and people working in these areas. So hopefully we can communicate these approaches and successes and limitations throughout and overcome them together. Question 9, on the slide mapping scheme basics, a lot of different sources are mentioned. How much of this data is processed automatically and how much is done manually? I want to get an idea how long it would take to create a view of building composition in a middle-sized town in an agricultural focused semi-rural region, in other words, not highly developed.
Okay, I spent a lot of time answering these questions, so but I think any of my colleagues can jump in anytime and give me a hand here. Really, how much money is spent developing the exposure database depends on many factors, including the risk of the town, the risk of the area. So that is, how much do you have to actually get it down? If it's in not a very risky area, you might be able to get away with not doing any development patterns and doing something like a hazards database or some global data set to look at the risk. If it's a very high risk town and you're worried about schools and hospitals, it can be a very extensive effort. But I think if we're specifically talking about the mapping scheme development pattern work, going to get local land use planning maps is a great place to start. If you've got tax assessor data, you can manipulate that to actually go beyond the need for getting some of these development patterns. But putting these things together in a few days to a week is very reasonable. There's a lot that you can infer from looking at high resolution optical data in Google Earth.
Yeah, I'll just add that, it really depends on the extent of the study. If you're looking at the entire country, you're not worried about every single structural type within that country. But if we're looking at a small town, the variations in the structural types and building heights will be pretty homogeneous at that point. So you're limited in what you need to look at. So your level of effort is much smaller.
Great, thank you, Mike. And question 10, are we going to get the case study PDF? Now, when I saw this come through, I thought possibly at first they were referring to the PDF of the presentation here today, but it is also possible that they could be referring to a specific case study and a link to that. So the person who asked that question, if you could drop in the question box a little bit of clarification, and if so, maybe we can find that URL for you. Question 11, is Google Earth Engine source code available? Is it possible to analyze your own satellite data in Google Earth Engine? Or can you only use data available in their catalogs?
Do you want to take this one?
Yeah, like say the source code, it's for the data, the source code that we use in Google, it's there. You can upload own data into Google Earth Engine. You can use that to process, but you have to check. You might want to check the licensing if you want to do any kind of commercial satellite data. You want to put it in Google. You definitely would like to check that and make sure that it's within your permitted use, and see also what Google does once the data gets into there. So yeah, but that's the short. But Google Earth, it's what we use. It's very basic in terms of what the engine provides in terms of being able to process that data. But yeah, if anybody requires some kind of sample, we can look into see what parts that's not proprietary we can distribute.
Yeah, thank you. And we had contact information in the contact slide at the end of the presentation. So, question 12, independent from population density, where we already have different global raster data sets, World Pop Land Scan, for example, is there any GIS global later indicating settlement vulnerability considering the urban structures? And I'll try to capture what you say here.
Mike, you wanna give this one a shot? You may be muted, or
we could also move on to question 13.
I can give it a shot. I don't think that there's any GIS data sets that capture that data. We've already mentioned several others that might be useful here. There's the World Housing Encyclopedia. UXGS has things by urban and non-urban areas. There's different places there, and then the GEM database. I'm not sure how public that is, but it's definitely a good place to have a look. It's GEM.
Yeah. Sorry, I was muted. Concerning urban structures, I mean, the Pager database has a tab specifically for urban structural types. So just be careful that a lot of these are using proxy cases. So you want to make sure that what you're looking at is essentially usable at that point.
Great, thank you. And this next one focuses on the case study. So possibly Z or Mike be able to address this one. What is the success rate of the Tunisia case study and the limitations? Maybe we need a little clarification on the success rate, but maybe you can comment to that.
Yeah, I think that's we're not sure what the success rate it's trying to ask. Maybe we could get a clarifying question on that. But for the Tunisia case study, like mentioned, where the goal was to have a view of the hazard for not hazard for the risk of the entire country for flood and earthquake. So for that purpose, we knew entering what the limitation of the analysis could be, because depending on based on the data that was used, so we could not do PMLs. We cannot do a return period assessment of the risk. We could only use the data that existed, the sources of hazard and that existed to do the risk analysis. So in terms of the exposure, we have some base exposure data that we used, and we used the methodology that we described to geospatially locate and say what the vulnerability is at different parts. So in that regard, we had a successful study, which we were able to produce the results that the World Bank was able to use. So that's the metric that we use in terms of for the success rate.
Great.
Ultimately, what the country of Tunisia used the data for in terms of their decision making, in terms of acquiring insurance and so forth, which is the ultimate success rate. We were not involved in those conversations, and it can be a frustrating thing often to not have access to your end client when you're doing these risk studies. But that's just the nature of the business, I think.
Great, thank you very much. Question 14. How can we consider the uncertainty in assessing exposure and vulnerability? And it's kind of a broad question here, but maybe just a little bit comment on uncertainty in general when it comes to these terms.
I think assessing the uncertainty of vulnerability is outside the context of what we're discussing here. There's a whole kind of science behind that. And I believe we do have another session where we talk explicitly about uncertainty in exposure, don't we, guys?
In part 3, we'll be talking more about that.
Yeah, so there'll be a whole session on that in part 3.
Yeah, but in terms of assessing exposure, there are many different aspects of that, which we'll be covering more.
Great. Even more reason to tune in for part 3 a week from today. Question 5. Morocco experienced an earthquake. How can I calculate damages post-earthquake? Any suggestions about the data sources and tools? And I'm not sure when this question came in, but I think that you did cover quite a bit throughout the presentation. So it's possible that you did go through some of these throughout the rest of the presentation. But if there's anything else that you wanted to comment on here, I can try to capture that.
Lee, you want to talk a little bit about which
yeah, I comment a little bit. I'll probably comment a bit. For earthquake, so for calculating the damages, you definitely need 3 different parts. One, it's the exposure, as we discussed in this particular workshop. We were focusing on saying the exposure. That means where people, buildings are located, what kind of vulnerability they have. Then you have to have the second part, which, given the vulnerability, what are the damage functions, right? What kind of damage would it suffer when you're subjected to the hazard? And the last part, of course, more importantly, where it's the hazard map. So for all 3 of component, you will need to have information on. So today's workshop focused more on the first part, which is creating that building exposure data. Then you have to have some engineering expertise to be able to determine what the damages are. And last, it's the hazard information that USGS does provide these type of information. USGS has a shake map program, which produces ground shaking levels ground shaking hazard GIS data that can be downloaded publicly accessible. But depending what region of the world it is, sometimes the accuracy you have to have it needs to be reviewed. So that's one source that you can use. Maybe if in terms of analytics tools, there may be some analytics tool already exists. GEM Global Earthquake Model, they do have tools that can be used for specifically for earthquake damage analysis. So that might be a source to look into. So USGS for hazard and GEM can be used for looking into the calculation. I think it's called OpenQuake. Yeah.
All right, great. Thank you very much. Question 16, how do you deal with mixed forms of building structures? When I was in North Africa, there was a lot of mixed buildings. Any comments on dealing with that?
I think I'll take a shot at that. Mixed buildings, I'm not sure what they mean here, but if they're talking in regards to mixed structural types, if that's what it is, we typically try to find a vulnerability curve that's specific to that. For example, if it's mixed, reinforced concrete with a URM infill, we'll have a fragility curve specifically for that. If he or she is talking in regards to mixed two separate structural systems, we will take the primary one as the primary lateral force resistance system as the one we model for our mapping scheme. Hopefully that's what he means by mixed. He or she.
Yeah.
Great. Oh, go ahead. Sorry.
Yeah, I think that's also where we create these development patterns, where within a pattern you have different type of buildings, all within the mixture, and we use the different statistics to determine what distribution of each of these types are within these patterns.
Great, thank you very much. On question 17, and we have room for a couple more before the top of the hour. Does hyperspectral satellite data analysis make analysis better than using broader spectral images?
Well, we've got a lot of research into hyperspectral data. We've some with plume modeling. It's something that I think would be very interesting for research. It couldn't hurt. So in terms of other companies doing this type of work, USGS, FEMA, NIBS, are doing this work from a federal perspective. I think it's widely recognized it's going to be much more important with climate change. And then there's commercial companies, ImageCat, AIR, RMS, and Moody's, CoreLogic. Lots of options here. So we can fill in this question with some.
Great, thank you. I live in the U.S. and I'm interested in doing this kind of work. What companies and organizations are doing this type of work? Or maybe you're already answering that question.
Yeah, I was trying to answer that.
Yeah, okay. We'll turn around and get to this. And what we'll do is once we clean this up and make sure everything is accurate, we'll post this on the training webpage for you to download. And you can have URLs there as well, possibly. And let's see here. Just briefly, did you go on the ground in Tunisia at any point during the study, or was it completely remotely assessed?
It was completely remote. On the ground, in a sense that we use the available Google Street View and Mapillary ground imagery, but we relied heavily on that and the field survey study from the University of Tunis, essentially.
Great,
Mike, you want to speak more generally about the difference between a study like Tunisia, where we're depending on remote data, and something like Costa Rica, where we went in the field?
Say that again, Charlie.
You want to kind of compare and contrast the benefits of going out in the field, like maybe looking at Costa Rica as compared to Tunisia?
Yeah, Tunisia, we were kind of hindered by the vulnerability curves that were available. So, we had all these different structural types, and we had to match any field survey to those structural types, and so we needed to use those vulnerability curves, as opposed to going out on our own. We can record what we want to use for our vulnerability curves. If we're looking at things like hurricane, we can start looking at any of these, roof types, hurricane straps, etc. But we're more free to gather the information that we specifically want, as opposed to relying on information that's kind of handed to us. So it kind of goes into where into the vulnerability modeling quite a bit. That way.
Great, thank you. And I see we're at the top of the hour, so thank you very much, Charlie, Gengiana, Mike, and Z. We really appreciate your time in this part 1 of the webinar series. We hope that you all join us for part 2 this Thursday, and then for part 3 next week. So thank you very much for joining us. We're going to close this for today. We'll post this recording hopefully within 24 hours if you want to go back and review anything, and we'll include this Q&A in the end of that video as well, and we'll post it on the training webpage. So I hope everybody else has a nice rest of your day, and thank you very much.